Hello everyone, this is Dr. Prashanthi, Assistant Professor of Chemistry from Government Degree College for Women, Karimnagar, Telangana State. Today I am going to discuss about the part 3 of amines. In part 1 and 2, we have seen the introduction, classification of amines, nomenclature of amines, preparation of amines, physical properties of amines, and in the part 2 we have seen the basic nature of amines and comparison between the basic strengths of ammonia and amines and alkyl amines and aryl amines and aryl amines and aryl alkyl amines, etc. we have seen. And then we have also seen the use of amines as a phase transfer catalyst also, and we have seen some chemical properties of alkyl amines and separation of amines by Hinsberger method in the part 2. And now in the part 3, let us see some electrophilic substitution reactions of aromatic amines and benzene diazonium chloride. About electrophilic substitution of aromatic amines. In aromatic amines, the lone pair of electrons present on nitrogen atom participate in the resonance stabilization. The reason for this is that amine group behaves as positive M group. In the resonance structures, the electron density will be more at ortho and para positions. On the whole, benzene ring will have more electron density. Therefore, this molecule participates in electrophilic substitution reactions actively. That is, suppose if you observe the resonance structures of aniline, for example, it is the best example for a simple aromatic amine. Aniline is a resonance hybrid of 5 structures, and in the resonance structures, maximum electron density will be present at ortho and para positions to the amine group. Therefore, amine group is ortho and para directing group, and it is a very powerful activating group. Let us see the resonance structures of aniline. See, this is aniline. Lone pair of electrons are present on the nitrogen atom of aniline. These lone pair of electrons are participating, they are not localized, they are delocalized and participating in resonance with the benzene ring. Therefore, they are participating in resonance with the benzene ring. So, here the electrons between these two carbon atoms are shifted to this carbon atom, giving it more electron density, and then again the electrons are shifted to NH2 plus. Now the electron density is more at this position, and then here now electron density is more at this position, NH2 plus, and now again the electrons are shifted back to the nitrogen atom of amine functional group. In this way, the electrons present on the nitrogen atom of aromatic amines is not localized, it is delocalized with the benzene ring. And if you observe in the resonance structures of these aniline, in the resonance structures of these aniline, we have electron density more at this position and this position. That is, these positions are, this is ortho position to aniline, this is para position to aniline, and this is ortho position to aniline. That is, electron density is more at ortho and para positions. Therefore, aniline acts as an ortho and para directing group. It is a powerful activating group. And therefore, the main problem that is associated with electrophilic substitution reactions of aromatic amines is that these are highly reactive, and therefore the substitution occurs only at ortho and para positions. But we do not get mono-substituted amine derivatives in these aromatic substitution reactions. Okay. In such case, the amine group, in such case, and in order to get only mono-substituted product instead of getting two products, that is ortho and para derivatives of aniline, if we want to get mono-substituted amine derivative or aniline derivative, first of all, the aniline group should be protected by acetylation. First, it is protected by acetylation, that is by treating it with acetic anhydride. So, when aniline is treated with acetic anhydride, this amine group is converted to amide group, that is NHCOCH3 group. It is converted to NHCOCH3 group. This is, and this group, now the electrons present on the nitrogen atom, they are less available for donation to the benzene ring, because they will be in resonance with the C double bond O of this CO group. Therefore, they are less available for benzene ring. Therefore, the activity effect of this group will be less than that of aniline group. And now the substitution or whatever the substituent we have to introduce, we can introduce and we can get a mono substituted product by protecting the aniline group by acetylation. So, in this way the electrophilic substitution reactions of aniline can be carried out. Let us see some examples what we have. Halogenation. Aniline reacts with bromine water to form 2,4,6-tribromoaniline. This reaction is called as bromination, that is halogenation means introducing halogen atom into the ring. But when aniline reacts with bromine water, 3 bromide ions are substituted at both ortho and para positions. That is polysubstitution occurs. Tribromoaniline, this is first position, second, third, fourth, fifth carbon, sixth carbon. So, 2, 4, 6, we have 3 bromide ions at 2, 4, 6 positions. Therefore, 2, 4, 6 tribromoaniline is obtained. And this halogenation of aniline takes place easily, and there is no need to use any catalyst in this halogenation. If we use chlorine, we get trichloroaniline by this method. Next. But as I have said just now, suppose if we want to prepare only mono derivative or mono substituted derivative, the amine group should be protected. Therefore, what we have to do, first it is treated with acetic anhydride. Therefore, this NH2 group is substituted by, or one of the hydrogen is substituted by the acetyl group. Okay, acetyl group, and then this acetyl or N-phenyl ethanamide or acetanilide, this is acetanilide. This acetanilide now reacts with the bromine and gives para-bromoaniline as the major product. So, to avoid polysubstitution, the activating effect of amine group should be diminished by acetylation. Otherwise, if this group is not protected, we will get a polysubstituted product. Next, nitration. Direct nitration of aniline is difficult again due to the formation of anilinium salt, and that gives meta-nitroaniline, because in the anilinium salt we have NH2 group is converted to NH3 plus, and it is a ring deactivating group and a meta-directing group. Therefore, direct nitration is somewhat a difficult process, and again it is carried out by acetylation only. And there is also another reason that if direct aniline is subjected to treat or subjected to react with the HNO3 or nitric acid in the nitration, this undergoes oxidation with HNO3. Instead of getting electrophilic substitution product, the NO2 group itself undergoes oxidation. Therefore, first we have to protect NH2 group, that is again by acetylation. Okay. So, first aniline in aniline, NH2 group is protected by treating it with acetic anhydride, so that we get acetanilide here. Now this acetanilide is subjected to nitration. Then we get ortho product and para product. Okay, we get a mixture of both ortho and para product. Therefore, aniline undergoes acetylation to give acetanilide, which on nitration gives ortho and para nitroacetanilide. This on treating with potassium hydroxide gives ortho and para nitroanilines. First we will get a mixture, then which on treating with KOH gives ortho and first we get ortho and para nitroacetanilides here, which on treating with the KOH they give ortho and para nitroanilines. In this way nitration on aniline is conducted. Next, oxidation of amines. Amines are oxidized in the presence of H2O2 per acids or KMnO4. See, here we have taken some examples of alkyl amines. So alkyl amines on oxidation gives aldehydes. Primary amines on oxidation gives aldehydes. Secondary amines, as they contain two alkyl groups, they undergo oxidation and gives rise to ketones. And tertiary amines, they on oxidation gives nitroalkanes. And mostly secondary amines are oxidized by KMnO4 potassium permanganate or H2SO5. This is Carros acid. Okay, and gives if secondary amine is oxidized with potassium permanganate, we get a tetraalkyl hydrazine as the product. And if secondary amine is oxidized with the Carros acid, dialkyl hydroxylamine is obtained. Actually this is hydroxylamine, NH2OH. If two hydrogens are replaced by two alkyl groups, it is dialkyl hydroxylamine. And NH2 is hydrazine. If all the hydrogens of hydrazine are replaced by alkyl groups, that is 4 hydrogens of hydrazine, if are replaced by 4 alkyl groups, then it is called as tetraalkyl hydrazine. So in this way secondary amines undergo oxidation with KMnO4 and gives tetraalkyl hydrazine, and secondary amines undergoes oxidation with Carros acid and gives dialkyl hydroxylamine. And coming to tertiary amines, these are oxidized by hydrogen peroxide and gives N-oxides. These are oxidized by H2O2 or Carros acid or ozone or Fenton's reagent. Whatever the product will be, N-oxides only. Next, oxidation of aromatic amines. Aromatic amines undergo oxidation easily with oxidizing agents like chromic acid and gives para-benzoquinones. So aniline on oxidation with the potassium dichromate gives para-benzoquinones. Next, diazotization. See, what is a diazotization? See, this is also a very important reaction in the under this topic. Aryl amines reacts with sodium nitrite in the presence of mineral acid at low temperatures to form aryl diazonium chloride salt. This process is called as diazotization. That is, here we will have, let us see, okay. Aliphatic diazonium salts are unstable, but aromatic diazonium salts are stable up to 10 degrees centigrade. See, these aliphatic diazonium salts are not stable, but aromatic diazonium salts which are obtained from our aniline are more stable up to 10 degrees centigrade. Okay, and these are unstable, these are when the reactions using the benzene diazonium salt are carried out in aqueous solutions only, because in the dry state they are very explosive in nature. Therefore, always their reactions can be carried out in aqueous solutions only. See, here is equation. Aniline, when treated with the sodium nitrite in the presence of mineral acid at very low temperatures, benzene diazonium, two nitrogen atoms are present in the compound, therefore diaza. So benzene diazonium chloride. Benzene diazonium chloride is obtained. General formula is aryl N plus triple bond N X minus, and with a lone pair of electrons. Next, what are the uses of a benzene disonium chloride? See, most of the reactions which are not carried out under normal conditions, or which are not carried out, or which cannot be carried out by the direct treating, they can be carried out by using benzene disonium chloride. That is, suppose for example, direct halogenation or direct fluorination on benzene is not possible. That is, fluorobenzene cannot be prepared directly by halogenation, but chlorination and bromination occurs easily, but fluorination cannot occur easily. Therefore, fluorination or introduction of fluorine group onto the benzene ring can be carried out by using this benzene disonium chloride. In this way, benzene disonium chloride is used in most of the reactions to introduce different functional groups onto the benzene ring. Let us see some of them. First one, replacement of disonium group by hydroxyl group. When benzene disonium chloride is warmed with water, phenols are obtained. That is, benzene disonium group is converted to OH group. So, when warmed with the water, it gives phenols. Next, replacement by cyano group. See, aniline is aniline again on treatment with the sodium nitrate and HCl, that is converted to benzene disonium chloride, and I already told you that benzene disonium chloride in dry state is explosive. Therefore, it can be stored in or the reactions using disonium chloride can be carried out only under aqueous solutions only. Therefore, these benzene disonium chloride is freshly prepared and used freshly for the introduction of groups. This benzene disonium chloride again on treated with the copper cyanide, it gives until disonium salt, disonium functional group is replaced by cyano group. In this way, cyanobenzene or benzonitrile is obtained. Next, Sand-Meyer reaction. Sand-Meyer reaction means the displacement of the nitrogen in benzene disonium chloride by either chlorine or bromide ions is called as Sand-Meyer reaction. That is, this group is replaced by either chloride ion or bromide ion just to form halobenzenes is called as Sand-Meyer reaction, and this is the most widely used or very convenient method for preparing aryl halides. Okay. Here, suppose if you see again, aniline is converted to benzene disonium chloride first, and benzene disonium chloride on treating with cuprous chloride in the presence of HCl, this disonium group is replaced by chloride group. If you take cuprous bromide, we will get a bromobenzene. Next, Gattermann reaction. See, this reaction is similar to Sand-Meyer reaction. This is similar to Sand-Meyer reaction, but this is carried out in the presence of a finely divided copper powder. See, there we used CuCl, but here we are using finely divided copper powder and HCl, and now this benzene disonium group is replaced by Cl group and we get a chlorobenzene. Next, replacement of disonium group by fluorine. See, in this method, generally I told you just now that direct fluorination is not possible on benzene, and the best method is by using disonium chloride only. From disonium chloride, this fluorobenzene is prepared very easily and conveniently, and for this again aniline is converted to benzene disonium chloride. Okay, this benzene disonium chloride is treated with fluoroboric acid, that is HBF4 fluoroboric acid. Okay, in this first fluoroborate is obtained. First salt is obtained, fluoroborate is obtained. Okay, this on heating and this on after heating it gives fluorobenzene. This is the best method for introducing fluorine group onto the benzene ring. Next, replacement of, and this reaction or the replacement of diazonium group by fluorine is called as a Sheeman reaction. And replacement of chlorine or replacement of diazonium group by by chlorine or bromine is called as Sand-Meyer reaction, and by fluorine is called as Sheeman reaction. Next, coming to the replacement of diazonium group by iodine. When benzene diazonium chloride is treated with aqueous solution of potassium iodide, iodobenzene is obtained, that is diazonium group is replaced by iodine group. And in all these reactions the nitrogen gas is evolved. This occurs with the evolution of N2. Replacement by nitro group. See, this nitro group can be introduced onto the benzene ring by using benzene diazonium chloride, and we can also introduce nitro group onto the benzene ring by the direct nitration on benzene with a concentrated HNO3 and a concentrated H2SO4. But this is also a very simple and easiest method that can be prepared from benzene diazonium chloride. And first here, as we have seen in Sheeman reaction, benzene diazonium chloride is treated with this fluoroboric acid. Again, as usual, we get a fluoroborate. See, if you see here, again we get a fluoroborate, but there this fluoroborate, if on heating, gives direct fluorobenzene. But if this fluoroborate is treated with the sodium nitrate and copper, finely divided copper, nitrobenzene is nitro group is substituted in the place of this borate salt. Okay. See, for fluorination, just if this borate is heated directly, we get a fluorobenzene. This is Sheeman reaction. But in order to introduce a nitro group also, we use fluoroboric acid, which gives borate, but this borate on heating with the sodium nitrite in the presence of finely divided copper, nitrobenzene is obtained. This. Next, replacement by aryl groups. See, benzene diazonium salts, when they react with any other aromatic compounds in alkaline medium, this diazonium group is replaced by aryl group. That is, this is replaced by this aryl group and we get biphenyls. Biphenyl is obtained. This method is called as Gomberg-Bachmann reaction. That is a replacement of diazonium group by aryl groups is called as Gomberg-Bachmann reaction. In this way, we can also introduce a phenyl ring onto a benzene ring also. Next, coupling reactions of diazonium salts. What are coupling reactions? See, in the alkaline or neutral solutions, diazonium salts reacts with the phenols or aryl amines like anilines. They undergo coupling reaction and yield the products, and the products, they retain this N double bond N group in them. These products are called as azo compounds. These are called as azo compounds, and this process is called as diazo coupling. See, the alkaline or neutral solutions of diazonium salts, when treated with phenols, or anilines, they undergo coupling reaction and they yield the products in which N double bond N group is present. Therefore, they are called as azo compounds, and this reaction is called as a diazo coupling reaction. Actually, these diazo compounds are usually, they are colored. They show or they contain bright colors, so they are used in identifying primary amines, and also they are used as dyes. They are used as dyes also in textile industries. Let us see one example. Benzene diazonium chloride on reaction with the phenol, here HCl is lost, in the presence of alkaline medium. Okay, this para hydroxy, see para hydroxy, this is ortho meta para, para hydroxy azobenzene. If two benzene rings are attached by n double bond n, that is called as azobenzene, and in this azobenzene we have one OH group at the para position, therefore it is para hydroxy azobenzene. This is a bright orange in color. This is used as a dye in textile industry. And suppose if you take example of beta naphthol, also we get this dye product, which is also a very, I think this is a scarlet red color dye with beta naphthol. Next, suppose if benzene diazonium chloride is treated with aniline, then we get a yellow colored product, that is see here aniline, this HCl is lost, okay, and in the para position we have a amine group, so para amino azobenzene, we know that this is azobenzene and we have a amine group here, so para amino azobenzene, which is a yellow colored dye. In this way, diazonium salts on reaction with the phenols and anilines, they gives rise to coupling products which have bright colors, therefore they are called as azo dyes and used as dyes in textile industries. Next, reduction. See, benzene diazonium chloride on reduction with the stannous chloride and HCl, they gives phenyl hydrazenes. See, this is a hydrazine, phenyl hydrazine. See, hydrazine means NH2, NH2. If one hydrogen atom is replaced by phenyl group, then it is phenyl hydrazine. Not only with the tin HCl, tin chloride and HCl, with the aqueous sodium bisulfite or with the sodium, zinc dust and acetic acid also, this diazonium chloride gives phenyl hydrazenes. So next, in this way benzene diazonium chloride gives different reactions, or benzene diazonium salts are very good intermediates for the introduction of all these groups such as fluorine, chlorine, bromine, iodine, cyanide group, hydroxyl group, nitro groups into the aromatic ring. So in this way the reactions which cannot be directly occurred on or the groups which cannot be directly introduced on the benzene ring can be introduced by using this benzene diazonium chloride. With this I concluded today's session of properties of electrophilic substitution reactions of aromatic amines, and also diazotization reaction and the uses of diazonium salts in the preparation of different benzene derivatives. With this I conclude today's session, and in the next session we will talk about the remaining part of the syllabus that is included in your BSc final year. Thank you.